On slide 17, I turn to Monte Carlo simulations to look at the reciprocal cross-legged model behavior. I'm going to do two kinds of simulations. First, here now, I'm going to talk about analysis where the data generation model is the same as the analysis model. So the H0 model is correct. Later on at the end of the talk, I'll do it differently. I'm going to generate by one model and analyze by another model. So for instance, if we generate data by the reciprocal model, we can ask ourselves, what would the regular RICLPM say? What would the estimates be? How much would we go wrong, so to speak? And vice versa, of course. On slide 18 then, here's the first kind of a simulation. And I'm going to work with parameter values that are based on a real data analysis. The first real data examples we're going to take a look at from the so-called MWI data, my work in I. And this is a data set from the ORT article. T equals 5, and I'm going to vary the sample size. In reality, its sample size is n equals 663. I'm going to generate normal data with no missing data, which is different from the real data analysis. And I'm going to estimate it by our reciprocal RICLPM. So random intercept, cross-legged effects, and reciprocal effects. And the cross-legged effects are going to be the same in the data generation, but the time invariance is not imposed in the analysis. The reciprocal effects are going to be time invariant in both data generation and analysis. I'm going to use bootstrap equals 500 draws to capture potentially non-normal distributions for the estimates and work with non-symmetric confidence intervals. I'm going to apply the non-duality reciprocal restriction, restriction B. I'm going to vary the number of time points as 3, 4, 5, and where the t equals 3 and 4 rounds are based on the first 3 and 4 time points of the MWI data set with 5 time points. Sample size varying as 500, 750, and 1000. And you will have the setup for this on the Webtalk website, where you can then, if you like, try other sample sizes, lower or higher. I'm going to focus on the quality of the estimates and the quality of the standard errors, as well as the power for both the bootstrap estimator and the MLR estimator. For all of them, the chi-square reject proportion is good. You know, the 5% reject should be about 5%. That is 5.05 proportion for the different replications should be, the outcome should be close to 0.05. And that happens in all of these cases very nicely. Now, on slide 19, I first take a look at the Monte Carlo distribution for a reciprocal effect, and we call it ST. That is the effect of, in this case, self-esteem on depression at the same time point t. So this is a contemporaneous lag zero effect. For a sample size of 500 with 5 or 3 time points, I was just interested in seeing how potentially non-normal it might be. Here's what it looks like for t equals 5, and on the right for t equals 3. And the skewness is fairly low. I mean, you see some skewness here, high values up to the right, but it's not that big, or at least not for t equals 5, a little higher for t equals 3, but not that high. What I conclude from that is that the maximum likelihood MLR CIs may be good enough, the non-symmetric ones. And for those who are interested how I did this plot in M+, I used the results option in the Monte Carlo command to save the estimates for all of the Monte Carlo replications. And then I followed that up by a type equals basic run, reading those data, and plotted these distributions. So on slide 20, we have a lot of information. So I'm going to take it in steps. The first column is then the parameter in question. So we have 3 parameters here in the first block. You have for time, this is S5 hat, refers to the within part of the self-esteem variable at time point 5. So it regresses on S4 hat, so that's the auto regression. In the population, that's 0.510. And here, regressed on D4 hat, that's the the cross-lagged effect, which is minus 0.158. And then you have the reciprocal effect, minus 0.091. Fairly low value here. And then you have a different set in the other direction, D on D. Auto regression is 0.214. Cross-lag with S is 0.059. a little bit lower than in the other direction. And then the reciprocal effect, much higher, minus 0.431. So S influences D more than D influences S here. In column 2, then we get the parameter estimates average over the replications. So for instance, if you look at the lag 0 effect here, we see that the estimate is fairly close to the true population value. And then the standard deviation is the variation across the replications, 500 replications in this case, that these estimates have. And you compare that then to the average of the standard errors by base and by MLR. So here I have sprinkled in an MLR column. You don't get that automatically in M+. So this column is bootstrapped and this column is MLR. The previous columns, average and standard deviation, are the same for bootstrap and MLR, because bootstrap parameter estimates are the same for MLR and ML. Now, and bootstrap. So then you see here that bootstrap tends to overestimate the variation in the estimates a little bit, and MLR does a little bit better in this case. 0.1028 is closer to 0.0966. And then over here, we're going to ignore MSE. We're going to mean square error. We're going to go to 95% coverage. This is for the bootstrap version, and that's close enough to 0.95, which we want. And then the last two columns, we have this percent sig coefficient. So those are the power columns where the MLR column is added. And we're talking about then the power to reject. That's, for instance, this this contemporaneous effect is 0. The power to reject that is 0. And we want to be able to reject that it's 0 with high probability, typically 0.8 or higher, you know. So here with bootstrap 0.844 and a little bit more optimistic value with MLR. So for bootstrap, this is based on the non-symmetric bootstrap confidence interval, which is a little bit wider than the symmetric one used for MLR, because you have a larger standard error estimate for bootstrap than for MLR, and perhaps also because the bootstrap is non-symmetric and allow for a wider interval that way as well. So this will be a 0.844 for bootstrap power, would be a conservative estimate, and the other one will be perhaps a little bit optimistic of an estimate. So going down, then this is for sample size 1,000, 750, 500. So even for 500, you get fairly good estimates. The population value is only slightly underestimated here, ignorably. The MLR standard errors are still better than the standard errors of bootstrapping. Coverage is good for bootstrapping. The power estimate for bootstrapping is quite low here, and closer to 0.80 for MLR. But I want to point out that even for a power of 0.56, you do have the possibility of a significant effect in any given sample in real data, for instance, as we will see, for lower sample sizes and for fewer time points. You can look at the ratio of the standard deviation, or rather the estimate of the standard deviation. 2 times 0.16 is 32, right? And you have then that's less than 0.42, which would indicate that there's a good chance to get significant results even for lower power values. Now, if you go to 4 time points, all of these power values go down. And for instance, if you take the more pessimistic bootstrap power value for t equals 4,500, it gets down to 0.6. And we have a real data example which is in that category. We get significant results even so, but you can't rely on it. For t equals 3, the power goes down further. And again, the bootstrap power estimate is less optimistic. So here's what you can work with and think about how you want to design your study. You should keep in mind that in real data you have missing data, so that even though this power here value 0.86 is nominally sufficient, it will be much less if you did this simulation with the trying to reflect the typical attrition over time. As we will see, real data have, of course, will have, of course, missing data with strong attrition. So you may want to have, you can study that with the model missing in M plus Monte Carlo, but you can imagine that you may need a bigger power value here to begin with in the non-missing data case.